Problem 10 is the half-life problem. It's my favorite problem. I love these exponential decay problems. And as we talked about in class, there's always two steps to these problems. One is they give you some information to figure out what the rate of decay is. And that's the K in this exponential decrease problem. We start with 120 grams of beryllium-7, whatever radioactive material that is, and it decays, fizzles down to 75 grams, and it takes 36 days. So that's not the half-life, right? It didn't go from 120 to half of that. It went from 120 to 75. So we have to figure out, that gives us some sense of how fast it's decreasing. We want to figure out how long until it's half of what it started, or in this case, 60. So we need to figure out the rate at which it's decreasing, and we do that by plugging in 36 and 75. 36 for the time and 75 for the amount. And we get this expression here. 75 is 120 times e to the k times the time, which is 36. Solve that for k, and we can get the exponential part by itself, the e to the 36k, and then switch to the logarithm version of that. The log of 75 over 120 equals 36k. Divide both sides by 36, and we end up with k being a really pretty small negative number. It's a negative because that makes the exponent negative, which makes it decrease. And it's small, meaning it takes a while for it to decrease. It's a slow decrease, 36 days to go to half. And so then you can plug that back into your formula and get that as your equation for the amount after t days. 120 times e to that negative rate times the time, times the number of days. But there's another way to think about that problem. That value for k, if we plug that in here and leave it in ln of whatever, rather than changing it to a decimal, what does that look like? Well, one of the things that's nice is, let's see if I can do that in here. I can play with this exponent, and the 36 t divided by 36, I can bring that outside and have that as a separate fraction. And I can then, one of the rules for exponents is I can kind of break that apart and do e to the ln of that, then that whole thing raised to the t over 36. And the nice thing is the e and the ln cancel each other out, so that we just get that that value of 75 over 120 that was in the exponent here, and it comes down here. So another way to describe this exponential decrease is I start with, let's pick a different color here. I start with 120, and I multiply by this growth factor that many times. So that means if t is 36, that means I multiply by one time. If t is double 36, that means I multiplied by 2, because that's two 36-day periods. So I could set this up. I didn't even need to do ln's. I could have written this from the beginning, this as a formula, and it's an equivalent equation, an equivalent expression. Just in this case, I can set up a nice base by saying, to go from 120 to 75, I multiplied by 75 over 120. That's my growth factor or decay factor. I don't have to use e to the kt if I don't want to. I could choose that as a base. And with that base, my exponent becomes t over 36. So in either case, I get an equation, and that tells me something about the rate at which it's decaying, either with base e or with a nice base like 2 for doubling, or 75 over 120, given the data I had. Then how do I find the half-life? The last thing is to set it equal to half of what I started, which in this case is 60. Or I could have just started and said a half equals the growth factor to a power. And again, in this case, I've got base e, so I switch to ln and solve for t. Ln of a half is going to be a negative number. Divided by that negative number ends up giving me a positive value for t, and it's 53. 53.07. The last thing I wanted to show you with this is what this looks like on a graph. We could say we started with temperature or with 120 grams of this at time 0, and we know the half-life is 53.07. So that should get us down to 60, right? Half of what we had. And the value they gave us was 36 days to get to 75. And so that's also on that equation. But you can also go another 53 days, 53.07 days, and you should cut it in half again, down to 30 this time. Another 53.07 days, and you cut it in half a second time. And so now you're down to 15, and so on. So that equation works out very nicely, and it matches exactly what the half-life is supposed to represent. So, but these problems are always a two-step problem. First one, you have to find an equation that tells you something about the rate. And then second, they can tell you, you can figure out what the half-life is. Some of the problems in the homework told you, here's the half-life, and then the second part was find when it's going to be some other value. And so those are really the same types of problems, just whether they tell you the half-life and find a different value, or find a different value and ask you to find the half-life.